Perfect. Thank you very much. So thanks very much for the introduction and for this opportunity to present the preliminary results of our project. Oh, okay. So as we are all well aware, the ground-based infrared instruments cannot compete with the space-based mission like Spitzer in terms of sensitivity and the wavelength coverage. However, they do offer great advantages in spatial and spectral resolution. For example, the VISIR instrument at VLT offers diffraction-limited images of about 0.3 arcseconds in the wavelength range from 8 to 13 micrometers, which is an order of magnitude higher than what could be reached by Spitzer. But perhaps the most defining characteristic of the ground-based observations in mid-infrared is the high level of background radiation that is coming from the atmosphere, the telescope, and its surroundings. And it results in a series of lines that are coming from telluric molecules, which drastically decrease the atmosphere transparency in certain wavelengths. So making the most effective use out of the ground-based instruments requires the knowledge of how the environmental conditions will affect the data. And in case of VISIR observations, a standard star is always observed in order to assess whether the sky conditions are good enough for the science observations to follow. And in case when the sky proves to be not in a good condition, we lose the telescope time. So our goal is to investigate if we could eliminate those telescope overheads by developing some kind of an empirical model that will help us to, that will be based on the ambient conditions and will predict the sky flux. And that would be extremely beneficial not only for VISIR operations, but also for the future instruments that are coming to Paranal, like CRIRES Plus and ERIS, as well as the METIS instrument coming to ELT that will operate at those wavelengths. And we would like to save the telescope time. So to do this, first we have collected several sets of the sky flats taken in the M band from two instruments located at Paranal. The first one is NACO, which operated in the wavelength range from 1 to 5 micrometers. And the second one is the VISIR, which is observing in the wavelength range from 5 to 24 micrometers. And for each observation, for each skyflat, we have extracted the current conditions of the sky at the instance of the observation. And the parameters we have explored are the infrared sky temperature, precipitable water vapor, relative humidity, mirror reflectivity, and so on. And all those parameters by themselves are loosely correlated with the sky counts. So this means that if we could combine all this information together, we could try to create a predictive model. And one of the tools that allows us to do this is called the principal component regression. PCR is a regression method that works in 2 steps. The first step is to perform a principal component analysis on the independent variables, which in our case are the ambient conditions, the humidity, the water vapor, and so on. And what PCA does, it extracts the most variation out of the data set. So if you will take a look here on this toy model, the first principal component will be maximizing the direction of the highest variance within the data. Then the second component, the second factor, will also maximize this variation. However, it by design will be orthogonal to the first one. And this process is iterative, so it will continue extracting the directions of the maximum variance until it exhausts all the dimensions of the initial data set. In our case, this is a 7-dimensional data set, so we will have 7 principal components. And then the second step is the performance of linear regression on the principal components that we have extracted in the first step and the dependent variables that we would like to predict, which is the sky counts. So since the principal components are directly related to the initial independent variables, we also will have a direct linear relationship between the original variables and the dependent variable, the sky counts. So these are the results of the first step of the principal component analysis, which we have applied to both NACO and VISIR. And as you can see, the variance in both data sets can be explained well by few first principal components. And in fact, we could get away with rejecting the last two components as they account for almost no variance of the data set, which means that they will bring no useful information for the model. So this way we can also reduce the dimensionality of our data sets. And to get a better idea of what the principal components are made of, we have created this correlation plot between the original variables and the principal components. And here you can see that the first principal component explains the variance in the mirror reflectivity parameter and the parameters related to the temperature. And the second principal component is correlated with humidity and precipitable water vapor, which do not contribute. Thank you. Which do not contribute to the first principal component. Air mass does not contribute to either of those components, but it contributes in a major way to the subsequent components. So with the principal components calculated, we could apply the regression. And so we have divided both data sets from NACO and VISIR into two subsets, which we call the training and test. And the training set was used to actually build the regression model. And then the test set was used to evaluate the regression that we have just calculated. And you can see that on this plot, I'm showing the actually measured values of the sky counts against what the model has predicted. And in case for NACO, the prediction error is quite low, it's around 2%. For VISIR, this case is slightly worse. The error for the prediction is about 4.6%. However, this is due to the fact that we didn't have complete information about the mirror reflectivity for those observations, which worsened the performance of the model. However, this also told us that this is a very important parameter that we have to for sure include in the future iterations of creating the predictive model. So this is the summary. Just wanted to highlight that with certain multivariate regression methods, like the principal component analysis, principal component regression, we can empirically predict sky levels to a decent amount, to the decent levels. And that can help us to eliminate in the future the standard star observations and save the telescope time. If you have any questions, I'll be happy to take them now, or we can discuss on Slack, or you can write to me directly. And thank you for your attention.
Thank you. I don't see a question in Slack still, so people are invited to ask this question. I have one question. You said that you get these numbers that you get are decent. What is your specification for decency? I mean, what is the goal?
We would like to create the model that will be as precise as possible. But I think that already for NACO, the 2% difference between the actually measured value and the predicted values is pretty good. Yes.
When you say that you lose telescope time, what kind of difference triggers a telescope time loss?
When the standard star observations show that the sky conditions are not sufficient enough for the subsequent science observations, those observations take about 15 to 20 minutes. When we cannot follow the science, this is considered as a telescope loss, which is globally about 1%.
Leonard is asking if you can try this with sensitivity, that means predict the flux calibration.
Can you repeat? I'm sorry.
Have you tried this also with sensitivity, which it means can you predict the flux calibration?
Not yet. This is something on the to-do list, but we will do it.
And Joseph Varga is asking, can this method be applied to spectra, for example, to predict telluric lines? And I support this question because we have this problem in Matisse.
I'm not sure. This is also something that we have to explore. At this moment, we haven't tried it, but possibly it could be done, I think.